Right, let's talk about Doppler's effect for sound. There are three separate scenarios. First, a moving source, stationary observer. Then there is a moving observer, stationary source. And finally, there is a moving source and moving observer. For this video, we're just going to focus on the first two scenarios, moving source, stationary observer, as well as moving observer, stationary source. So let's begin. First, let's look at moving source and stationary observer. The moving source is moving with a speed u subscript s and emits sound of frequency f, and the speed of the sound is v. So there are two separate cases in the first scenario. The moving source is moving towards a stationary observer, or the moving source is moving away from a stationary observer. So let's look at the first case. Imagine I have an ambulance moving towards a stationary observer. It gives off sound, as shown here, the wavefront moving forward, and the ambulance, the source, is moving with a speed u subscript s towards the stationary observer. This is the first wavefront emitted. So let's derive a formula for the observed frequency. In 1 second, imagine the distance moved by the first wave front would have been the speed of the wave multiplied by the time, 1 second. So it will be v times 1, which is v. Similarly, in 1 second, the distance moved by the source will be u subscript s times 1, which is u subscript s. Also, in 1 second, the number of wave fronts that are emitted. Remember, the frequency for sound is f. So in 1 second, f number of wavefronts are emitted. And in 1 second, the distance between the first wavefront and the source. Imagine the first wavefront is moving ahead, and the source, the ambulance in this case, is moving right behind. So the distance between the first wavefront and the source would have been v minus us in the first second. So therefore, the observed wavelength, lambda O, will be given by, imagine the distance that has to contain f number of wavefronts emitted would be v minus us. So this is the distance that will have to squeeze in f number of wavefronts. So the wavelength observed would have been v minus us divided by f. And therefore, the observed frequency f naught would have been v, the speed of the wave, divided by the observed wavelength. And this will work out to be f v over v minus us. Now let's look at the second case for the first scenario, where the moving source is moving away from the stationary observer. So I have here the observer stationary and the ambulance moving away. And similarly, the wave front is given off by the ambulance. An ambulance moving with a speed u subscript s. Now notice the distance between the wavefront here, lambda 2, and the wavefront here, lambda 1, is different. So lambda 2 obviously is bigger than lambda 1. So let's analyze. Similarly, in 1 second, the distance moved by the first wavefront would also be v. The distance moved by the source in 1 second is also u subscript s. And in 1 second, f number of wavefronts are emitted. Next, in 1 second, the distance between the first wavefront and the source. The earlier case, the distance is smaller, is squeezing in. The source is chasing after the first wavefront. In the second case here, the source is moving away in the opposite direction from the first wavefront. So the distance in 1 second between the first wavefront and the source would be v plus us. So therefore, the observed wavelength similarly would be this distance occupying this number of wave. So it would be v plus us divided by f. So finally, the observed frequency f naught would be v over observed wavelength, and it would be f v over v plus us. So this is the equation for a moving source moving away from a stationary observer. So let's combine the two together. The observed frequency for moving source and stationary observer would be f v over v plus minus us. Okay, so this is the equation for a moving source. Let's move on to the second scenario. A moving observer with a speed u, in this case is O. O stands for observer, and the sound emitted is of frequency f and speed v. So let's look. There are two cases for this scenario again. One is the moving observer is moving towards the stationary source. The next is the moving observer is moving away from the stationary source. So here I have the ambulance, in this case not moving, stationary, and it's giving off wave fronts. The observer now is moving towards the ambulance with the speed u o. So in 1 second, the distance traveled by the observer would be u o times 1, which is u o. And in 1 second again, the number of wavefronts emitted by the ambulance is f. The wavelength of emitted wave. So what is the wavelength of this emitted wave? It would be the speed of the wave, v, divided by f. As recall from v equals to f lambda. So we are looking at lambda equals to v over f. So in 1 second, the number of additional waves reaching the observer. Remember, in this case, if the observer is stationary, f number of waves would have reached the observer in 1 second. But now, the observer is moving forward towards the source. So there are additional wave fronts reaching the observer as a result of him moving forward. So in 1 second, the number of additional waves reaching the observer would have been this distance divided by this wavefront. So it will be u subscript o divided by v over f. And this works out to be f u naught over v. So now let's consolidate. In 1 second, the total number of wavefronts reaching the observer. So this is the additional one. This is the number that would reach the observer if it's not moving. So the total number now would be the addition of both. So it will be f plus f u naught over v. And if I may factorize, I get this. And now, what is the observed frequency? Observed frequency f naught is essentially the number of wavefronts reaching the observer in 1 second, which is the same expression as this one, number of wavefronts reaching the observer in 1 second. So I can rewrite that, but let me just rearrange that a little bit and make it to a common denominator, v. So this is for the case of moving observer towards a stationary source. Let's look at the next case, moving observer away from the stationary source. So again, the ambulance is stationary, and now the observer is moving away with speed u subscript o. Notice in this case, lambda 1 and lambda 2, they are the same because the source is stationary. So let's analyze. In 1 second, the distance traveled by the observer again is u subscript o, and in 1 second, f number of wavefronts are emitted, and also the wavelength of the wave emitted would be v over f. So in 1 second earlier, number of additional waves reaching the observer, because the observer is moving towards the source, there are additional waves. Now the observer is moving away from the source, and therefore the observer is escaping from the incoming wavefronts, so there is less number of waves reaching him because he's walking away. So in 1 second, the number of waves reduced from reaching the observer would be, again, this distance u0 divided by this wavelength v over f. So it will be f u0 over v. So in 1 second, the total number of wavefronts reaching the observer right now is less. So it would be f when he's stationary, subtract when he's moving away. And that, if I factorize, I get 1 minus u0 over v. So what is the observed frequency f0? Observed frequency f0 would be essentially this expression over here. So allow me to make that to a common denominator, v minus u0 over v. So now I have the two cases for scenario B. So let's put them together. The observed frequency for moving observer stationary source would be f v plus minus u0 over v. So I hope you gain an understanding of how these equations are derived. Thank you.